Starting from scratch with Scala Native. So this is a talk about Scala Native. You're in the right room if that's what you came here for. It's also, this is what I'm trying this time, is to just give sort of an introduction to systems programming, sort of from the ground floor in Scala, and in Scala Native in particular, right? And in getting there, I think it's also become a talk just about working with emerging technology. Scala Native is surprisingly robust, but also still quite new. It's also just about learning to rely on your operating system and your machine itself as a platform for writing code on, rather than the Java virtual machine and frameworks and runtimes that we've sort of come to rely on over the last couple decades. Or in other words, this is a talk about how to get things done without the JVM. So in terms of the actual content, I'm going to start with a really quick introduction. This is what Scala Native is, and then spend a fair amount of time just talking about how to work like close to the metal. Like, what does it mean to work at a lower level without a virtual machine doing work for you. And then we're going to go right from there into writing a real program with real data at scale. We're going to take the Google Ngrams data set, which I'll talk a lot more about when we get there, and work through a few simple algorithms on it. Sort of a maximum finder and also a sort. I don't think we're going to have time to get to the aggregation, but we'll see if I go really fast. And for all of the algorithms, we have performance numbers comparing our Scala Native implementation to a vaguely equivalent vanilla Scala implementation. So we'll have some empirical basis for looking at what we've done. And that'll conclude the empirical observations, and then I'll wave my hands and make some wild speculations about the future and broad trends, as one does. About me, I'm a Scala Native contributor, but I'm speaking only for myself here, and I'm not a member of the core team. And I can't speak for where Dennis or Martin see it going. I am the author of Modern Systems Programming in Scala, the first book about Scala Native. It's coming out hopefully this year from Pragmatic. And I'm a data engineer at M1 Finance in Chicago. Obligatory plug, M1 Finance is a simple, powerful, free way to invest. And we have an awesome app. Come check us out. And I'm on Twitter at Richard Whaling, and I tweeted out these slides. I tweeted out my Strange Loop talk from last year about how to build a web server in Scala Native. And I tweet lots of animal memes and stuff too, if you like animals. So yeah, without further ado, let's get started. So Scala Native, we love it because it's Scala, right? Much like Scala JS, Scala Native is a Scala C plugin. Basically, it patches the Scala compiler to emit LLVM bytecode instead of JVM bytecode. The reason that becomes an ahead-of-time compiler, right, is if for people who are less familiar with it, LLVM isn't a runtime virtual machine the way the Java virtual machine is. It's really more of a compiler framework. So it eventually generates machine bytecode. The Rust compiler runs on LLVM, Clang, Apple C compiler runs on LLVM, et cetera, et cetera. When you're just emitting like a compact, like 3 or 4 megabyte native binary like this, you get programs that start up much faster in like tens of milliseconds instead of, sometimes seconds waiting for a JVM to boot all the way up, right? So for command line tools, it's great. Tools like Scala Format, Scala Fix, things like that are obvious low-hanging fruit for Scala Native, right? Scala C itself has been seen running in Scala Native, which is pretty cool. But the trick and the trade-off with that, right, is that you lose the JVM. A lot of the JVM facilities that you come to rely on are gone. You lose a lot of JDK classes. You definitely lose things like dynamic class loading and stuff like that. So getting something like SBT itself to run in Scala Native is probably going to be a lot harder. That said, Scala Native, much like Scala JS, does include implementations of several hundred JDK classes, enough to make a large proportion of like relatively straightforward programs just sort of run out of the box. But if something is missing, you can also implement it yourself, or just implement awesome other stuff like we are going to today, because it provides this really amazing set of types and functions for interoperability with C programs, but also just for writing Scala programs with broadly equivalent power to like C or Rust or something like that. And writing those kinds of programs is sort of what this talk focuses on, rather than just, hey, switch your SBT, add a compiler plugin and recompile your program. This is about how to like really lean into programming for Scala Native. But for the basics, right? Like this, like trivial Scala hello world, this just works in Scala Native. This will compile. It'll print out about. It'll print out a little more diagnostics from your SBT, as it's actually doing quite a lot of work to generate a native executable binary, but it eventually spits out a 4 megabyte file that prints hello Scala Days, right? However, you can also go a little bit deeper. You can import the Scala Native.native package, and then you can import standard IO from there. And then all of a sudden you have this, you have printf. Just so I can sort of gauge the audience, who here's used printf? Cool, all right. Yeah, so this isn't like a wrapper. I've looked at the LLVM intermediate code for this. When you do this in Scala Native, it's literally invoking the glibc printf function, right? And it's doing that because when Scala Native uses types that are compatible with C, which things like ints and floats just work, for things here we're using like C strings instead of regular strings, and you'll see, right, that I'm putting a little C in front of the string literals to tell it to build C strings. That's because those are actually strings the way they work in a C program, which is exactly as awful as it sounds, as I have quite a few slides today to discuss. But it means you can like throw around strings, pass them to printf, and do IO as quickly and as dangerously as one does in C, for better or for worse. But to even like talk about how one really like writes programs like that, much less writes them safely, I want to just sort of take a step back and throw some of the fundamental concepts out, maybe more as a refresher, just because me talking for 10 minutes isn't going to be the equivalent of like a couple of weeks of coursework. But I think Scala Native really packages up a lot of these concepts in a way that's cleaner than they're usually taught. So I have high hopes. So the most important thing is that there's a pretty small number of data types that are actually primitive. Ints are primitive of various sizes, signed and unsigned, floats, and bytes themselves, which are really just, unfortunately, they're signed ints for compatibility with Java, which is really regrettable. But they're sort of the most primitive data type of them all, right? Any unmanaged data that's outside of the domain of the garbage collector, right, is going to have an address. And that address can be represented by a pointer. And a pointer is just, in any modern environment, that's going to be an 8-byte unsigned integer. It's just the numeric address in memory where the data happens to live. Because these pointers are themselves numeric data types, you can do arithmetic manipulations on them. And if you structure your data to support it, right, a huge number of things that require multiple lookups, cache misses, and indirections in higher level languages are pointer arithmetic. In C or in Scala Native, which can either be done at constant time or often just computed at compile time, in fact, entirely statically. Pointers are typed. You'll see in Scala Native, a pointer is just a generic. It's great. But you can cast them to other types. That's a compile time coercion, right? That's not like a runtime. It doesn't introspect the data at all. It's purely just changing the type to make things line up, which to us Scala developers, right, is something to be avoided, but when you're working with C APIs, it's often necessary. A large number of legacy C APIs, including like the BSD sockets API, just require you to like brazenly coerce one type to another, even when they aren't in like a union or anything like that. It's called type punning, and it's really painful, but sometimes you have to do it. And the other thing that casting does in situations like that is it lets you basically emulate a lot of the functionality and behavior of a more robust type system. You can build like things that resemble union types or more abstract types or inheritance and things like that awkwardly. And I don't think we're going to get too deep into that, but you should know it's there because we will see some sort of generic programming patterns a little later on. So those are the basics. We also need to talk about like a handful of like low-level like compound data structures. The first and probably most important one is a struct, which is a lot like a case class or a tuple product, right? named typed fields. The difference is the order of the fields and the size of each of those fields is static, right? So the address of any field of a struct is also, again, known at compile time just as an offset from the address of the start of the struct. And then you also have arrays, and I think most folks are familiar with arrays. And honestly, arrays are not that far from Java arrays, right? It's an index sequence data structure. The difference is it does refer quite directly to a particular block of contiguous memory that only contains items of the exact same type that are of the exact same size. Because they all occupy the exact same amount of memory, you can also just compute the position of any item in your array, again, statically, just by multiplying the size times the index that you want. And we'll actually do that ourselves shortly. Again, both of these are constrained that the only things you can put into these compound like low-level data types are other things that have like a statically known size. So like primitives, pointers, arrays, and structs, basically, you can't put a case class into an array, for example, much less or objects or regular classes and things like that. So it ends up creating sort of a bright line in the type system between sort of the unmanaged Scala native classes and the higher level, like regular vanilla Scala classes that still have like normal semantics and garbage collection and stuff like that. Finally, we have to talk about strings because in C and in Scala Native, strings are not a first-class data type. A string is just a pointer to some bytes somewhere. And in particular, they function like arrays, but because we actually lose any runtime knowledge of the size of arrays, right? Strings are painful and dangerous to work with. And figuring out how to do it safely is not awesome. But it's sort of the first thing you have to do even to write a functioning Hello World program. So C strings work like this. Basically 1 byte per character, laid out one after the other. And the way you know where the end is if you look at the end, you have the binary 0 as the last character after the exclamation mark. Basically, this is how C strings indicate their length. You have the address of the first character in the string. That's the value of the C string is, in fact, just the position of the first character. And if you have a string manipulating function, it just reads until it reaches this terminating mark. And of course, the way this can go horribly wrong is if you forget to add that terminating mark onto the end, your string manipulating function will happily go off the end into some unsafe piece of memory until it encounters something else that looks like a binary 0. And this happens so much because the C standard library is so broken. Fortunately, we are Scala developers and we're good at abstraction and we can do better than this. And we can protect ourselves from this. But I am going to have to complain about this a lot for the next 30 minutes or so. Under the hood, like if you look at the Scala native built-ins, C string is actually just a type alias for a pointer to a C character, which is actually, and that it's really just an alias to pointer to bytes. It's about as primitive of a representation of a string as you get. The other thing to call it is that they're mutable. It doesn't really behave like a good, well-behaved, immutable string like we typically get in modern languages. This also makes it really powerful for doing like zero copy I/O and stuff like that. But you have to be cautious with it. So we can write like a simple program that shows some of these properties, right, where we just take a string, we calculate its length with the C string length function. We can print some diagnostics about it, but then we can also just sort of iterate over the string. And I think, yeah, there we go. So the idea is once we know the length, we can just iterate over the characters in it, one character at a time. And then we can access them by just grabbing them the way we would any other indexed sequence. The difference, right, is because this is just a pointer dereference. If you go off the end, this is not going to throw a nice, clean, like, array index out of bounds exception. This might segfault. It might return garbage data from somewhere else in your stack or your heap. You want to be really cautious when you're working with arrays directly. But it's also frighteningly fast. And in general, it's going to be constant time. The other thing is that, again, because it's just pointer arithmetic, we can do this ourselves. And I decided to rewrite it this way, just so we could just see the two important pointer arithmetic operations at work. So our code's basically the same. What we're doing, though, is instead of just grabbing a character in one step, we're doing it in two steps. First, we're computing the address of the character at the index we care about, right? So we take the base address of the string, and we add the offset to compute the address of the character. And then to actually get the value of the character, we dereference it with the exclamation mark or bang operator. It's equivalent to the asterisk in C, right, for people who've seen C or Go or something like that. So when we run this, we'll see something like this. And not to like linger over a bunch of like hexadecimal gibberish, but I think this actually demonstrates some cool stuff, so I just wanted to call it out. First of all, the string itself, right, like the content of the string, according to string length, is 12 bytes long. But if you were to count the lines here, there's actually 13 of them, because string length does not count the terminating 0 byte, which is necessary for the string to function with integrity, right? So there's 13 bytes to store a 12-byte string. It's very important to remember. And then the actual value of the string itself is just a pointer, which means it's the value of the string is just 8 bytes. It's precisely this hexadecimal address. But if you look, the address is literally the same value as the address of the first character in the string. There's no way to distinguish those two things are the same as far as the type system is concerned, which feels a little bit like a paradox, but it is surprisingly elegant once you learn how to work with it. So that's enough of me talking about how terrible strings are. We also need to talk about memory allocation. Like I was saying earlier, when you're using regular Scala classes, case classes, things like that, the Scala Native's garbage collector is in full effect, and it runs great. When you're working with these C-compatible types, you can do stack allocation and heap allocation, just like you would in a C program. Scala Native also has this really cool zone allocator, which is awesome. I don't have time to cover it today. The neat thing, though, that Scala Native does that Go and Rust and C don't do is stack allocation is actually explicit here. Which is surprisingly innovative. It means you don't have to do an address of operation ever. And it makes you much more formal about where you're pulling pointers off the stack. It makes it much harder to leak them. The really thing to remember about stack allocation is that it's literally allocating some number of bytes of memory for you on the like machine level call stack. And it is only valid until the function that allocates it returns. Once you return, that stack frame no longer exists and will get reused the next time some other function calls that deep into the stack, right? So leaking a pointer that just has the address of somewhere in your stack that's been clobbered a couple dozen times is a classic C programming error. It's pretty hard to do in Scala Native, again, just because we've made it explicit here. Also, the nice thing here is that it's taking type parameters, which is a lot cleaner than good old malloc, which is why we should talk about malloc next. Who here's used malloc? Yeah, it's notorious. It's kind of unpleasant, but it works. It's a lot lower level than the way Scala Native implements stack allocation. But the C implementation takes an integer as an argument. You'd say, hey, this is how many bytes I want. It gives you that many bytes back. And in C, it'd be a void pointer. Scala Native doesn't have void pointers. It just has a pointer to bytes, which I think is much cleaner, actually. But it also doesn't have any like implicit casts on that. So you'll see what I'm doing here is if I want a pointer to a buffer of 3 ints, I malloc 3 times the size of an integer, and then I cast that to a pointer of integers, right? And that's actually a little more verbose than C is, but I find it's actually a lot cleaner and safer. The other thing about arrays, right, is these are index sequences, but they're of a fixed size unless we manually resize them. To resize them, we use realloc, which is usually pretty obscure, but we're actually going to use it in like about 10 minutes to sort of write a slab allocator kind of doodad. Basically, you have to cast your array back down to a pointer of bytes, pass in the new size, and then cast it again. So there's 2 casts there. That said, again, we're in Scala, we're good at abstraction. So if we wanted to write like a heap alloc function that had more like the ergonomics of stack alloc, it's right here, it's a one-liner. You just take a type parameter, how many things you want, easy. And you'll see we can abstract over like a growable array pretty easily in a second. Also, realloc is dangerous. You always have to free your pointers. This isn't the time or space for me to continue ranting about that, but I do have to say free your pointers. And the last thing sort of on the C interop angle I want to talk about is the foreign function interface that Scala Native provides, which I think is really slick. Like I've been doing like C FFI kind of stuff for most of my career, and this is probably the best one I've ever used. If you want to import a function from either the C standard library or just a third-party C shared library you found on GitHub, this is how you do it. All you have to do is translate its signature to a Scala Native signature. There's a table in the Scala Native docs for doing the translation. And then you just put it in one of these extern objects and supply extern for the value of it. And that's literally it. Then when you invoke it, Scala Native will invoke the function you hooked it up to. And it works pretty magically. Here, I'm actually just hooking it up to some C standard library functions. Most of these are actually provided in the standard I/O package, and most of the things you'd actually use are, but like in my strange loop talk, I wrote bindings for most of libuv, the Node.js event loop library, and it's just about as simple. Really, really powerful stuff, and it really gives you superpowers, especially in the absence of like the JVM and the things you would otherwise rely on. Probably there's a couple C functions we should talk about before we move on, just so people have seen them. We've seen printf. fgets is probably the only string I/O reading function I would actually recommend using. It reads a line of text from standard input into an array of some maximum size. It takes an argument for the maximum size to read, which is really good because it prevents you from overflowing off the end. scanf is sort of the inverse of printf. It reads data from, it's a formatted input function basically, that reads data from a string into more structured memory. And it takes a format string just like printf does. We'll see some examples of it shortly. And then for actual string manipulation functions, we're going to use string comp a bit, just for, it's a comparator. It returns negative, 0, or positive based on whether one string is less than, greater than, equal to the other, like any comparator would. And then notoriously, all of the functions in the C standard library for copying strings are broken. The string copy is the least broken one, but I actually found I couldn't use it safely, and there will be a wrapper around it in the couple of places where I use it here. I had to cut the slide or actually derive the wrapper, but it's, yeah, so this is the moment where I take a breath, check my time. How are people doing? Are people feeling good about this so far? I'm not going too fast? Cool. So we're going to write some real programs now. This systems programming is never trivial, but I mean, the reason I'm writing a book about this is that I do believe that Scala Native does present it in a way that's actually more clear than C. That working with the language that really supports type parameters is a real thing, makes it work. Also, Scala Native's compiler is totally state-of-the-art. I think like Thursday or Friday, Dennis tweeted out some numbers for the new optimizer that are sort of breathtaking. It's moving really fast. But I get really excited where Scala Native lets you write programs that you couldn't with vanilla Scala, where you're really like opening up the hood and working at a fundamentally lower level, which isn't something that a compiler really gives you. And treating Scala Native as a DSL for writing C in some ways is sort of where my heart is. And it's going to let us write programs that are pretty different, but also have some interesting performance characteristics. So to show that, though, we need some real data. Google Ngrams is this 50 megabyte data set that's word counts for the entire Google Books corpus. It's tab-delimited text files, 4 columns each. They're separated by the first letter of a given word, so like just the A words is 2 gigabytes, and that's what I'm going to use today, just in the interest of sanity. And we're just going to write some pretty simple algorithms that work on this non-trivial data set and see how it scales as we throw more data at it, basically. So like we're going to find the maximum word count. We're going to find the top 20, which is actually we're going to treat that as a sorting problem. I don't think we have the time to mix sorting and aggregation, but there's a really cool like sort of in-place accumulation hack you can do there. The files look like this. They have the word. A lot of the words have part of speech tags. This isn't an NLP talk, so ignore the part of speech tags. It has the year. It has the count. And then the last column is the dot count, the number of books in which it occurs, which you'd need for like TF-IDF. This isn't an information retrieval talk, so we're going to parse it, but we can ignore it. The one we care about is the actual number of occurrences, that third column there. So I'm going to say if we're going to write like the most naive like vanilla Java implementation of like how to find the maximum word in a file like that, it would look something like this if we're not being especially idiomatic and using vars and mutating state and all that. Just walk through standard in, split things on white space, convert the count to an integer, and then just compare our count and mutate our state when necessary. And this works. It's not super fast, but it works. To do this in Scala Native, we should strategize before we write code like this. When you're working close to the metal and managing memory yourself, it's incredibly important that you have a plan of attack and a discipline guiding the way you're using memory before you write your first line of code. Once you have that strategy in place, it's a bit tedious, but it works. Our plan is to only allocate enough memory for the current maximum that we've seen and for us the single line of current input. That's all we need to allocate, right? And then we're just going to recycle that data as we go and try to get our allocations as far down as we can, right? Because we're going to have to parse 2 gigabytes of data, about 86 million rows. So avoiding allocating 86 million strings, right, is going to give us a lot of performance. So the idea is we're going to use fgets. We're going to read one line at a time from standard input into our line buffer. We're just going to cap it at 1,024 characters to be safe. And fgets returns null when it's done, so this will just read until it reads everything. And this is a weird little C idiom that I wanted to call out. So one thing you can do with pointers and C is you can treat them like arrays, right? But you can also just treat them as mutable cells. And passing a pointer into a function that doesn't return anything in idiomatic C, right, is a way to indicate I'm passing these things in, especially if it's uninitialized, because it may or may not get overwritten while this function executes, and it might be in a different state when this function returns. So to avoid allocation, what we're going to do is we're going to allocate the count, the word, and the year outside of our actual scan and compare function that's parsing them. And we're actually going to do the comparison inside there and assign back out, which is we're very idiomatically in C territory here. In the next example, we're going to go a little cleaner, but I did want to really do a one-for-one port here. The scan and compare function ends up being about as long as the main routine. We have to stack allocate again, right? Just to get temporary storage for the count, the word, and the year. The cool thing with stack allocation, though, is it's basically free. You're just bumping a stack pointer, and in general, the compiler knows exactly how much memory is getting allocated for the invocation of this function. So it's about as free as allocation gets. We're going to use scanf to just scan directly into the pointers that we've allocated here. This temp word, temp count, temp year, and temp dot count. We have to check that we matched 4 things because scanf is insane, and instead of having exceptions, it will happily just give you partial or garbage data, but that's a whole other rant. And then once we have it in our temporary storage, then we can actually do our comparison and decide how to update the permanent storage. And this is actually worth stepping through a little bit because it's idiomatic. We're doing a dereference on both the left-hand side and the right-hand side of an assignment, right? We're saying dereference max count equals dereference temp count. What that means is that it's going to first dereference the pointer temp count to get the value that we've read into the pointer, and then it's going to assign that to the memory pointed at by the max count pointer. right? So basically it's dereferencing one mutable cell and storing into the location indicated by another mutable cell. That works for count and year because they're both numeric and atomic values. If we were to try to do that with a string, though, we wouldn't get the behavior we want. A string is just a pointer to bytes. So when we dereference a string, the result of dereference of just an exclamation dereference or an asterisk dereference of a string is just going to be the first character of the string, and then it's going to store that at the address of the first character of the destination string. Not what we want at all. This is where we have to use a string copying function, and all the standard ones are broken, so I wrapped it. But I'll have to save that for another time because I'm a little behind and I don't think I can show you how to wrap it. But string, I really want to replace the entire C standard string library. So once we've written this, we're basically ready to write our code. And when you run this on like 100 megabytes of data, the performance, Scala Native's a little bit faster. All of these numbers, I cut out the JVM startup time. I didn't start the timing until after the JVM was fully booted and actually executing Scala code, right? So we're actually giving the JVM a moderately unfair advantage here. Native still beats it with 100 megabytes of data. It ran Native's in like 4.7 seconds. The JVM's in like 5.4. But this actually diverges as we throw more data into it. So by the time we're at 500 megabytes of data, the JVM's in about 29 seconds, Native's at 15 seconds, so twice as fast. By the time you get up to 1100 megabytes, Java's 90 seconds, Native is 30 seconds. By the time you get to 1700, which is basically the whole file, the JVM's running it at 186 seconds, that's 3 minutes. And Native's in 43 seconds, so about 4 times faster. So you see, we're not talking, oh, Native is 5% faster than Hotspot or 10% faster. We're really talking about things that diverge over time, that look pretty nonlinear to me, honestly. So this is exciting, but it's also a little trivial, right? We're doing almost no allocations. We're sort of using some weird C idioms. And we're a little bit off. You couldn't think of a better example for Native kicking the JVM's butt to use strong language. So let's come up with something a little maybe that tests some different conditions, I guess. Now we're going to sort the exact same file. This is going to use heap much more intensively. This doesn't generate garbage, right? It's just reading a bunch of data and keeping it around. And that's the inverse of the performance characteristics of the last program we wrote. To solve this, well, to do this in Java, I'm just going to use an array buffer. I'm going to actually create an Ngram case class to store these things and model them. But otherwise, the code's pretty much the same. And then for the actual sorting code, just sorting the array buffer, right? Doing this in Native is, again, we want to be strategic. We're going to create a struct to model our Ngrams. We talked about structs, but I didn't show you the syntax. I'll show you that really quick. We're going to read that into an array. And of course, we're going to have to resize that array as we go because we don't know how many things we're going to read. That's kind of tricky to do, but we'll see that we can wrap it and make it sane. And then we're going to sort it. To do that, we're going to need not just structs and malloc and realloc. We're also going to need qsort, the C standard library quicksort function, which is really fast and really powerful, a little tricky to use, but awesome. Just really quickly, structs work like this. In the current release of Scala Native, struct fields aren't named. They're treated more like tuples. That's changing whenever the Interop 2.0 version, which I think is the 0.4 release, comes out. And then structs will have named fields like case classes. The structs we're using here are small, so it's not something we really need to worry about, but just to call it out is something that might be a little odd if you look closely at the code. And just reminding that the fields are laid out in contiguous memory, like literally like one byte after the other, which turns out to be really great for like cache locality and stuff like that. Then, yeah, so to actually model our Ngram as a struct, we just do it like this. It's a struct containing a C string and 3 ints. The one thing that's tricky is that string, right? Because it's a string of variable length. You can't really fit a string of variable length inside the contiguous memory of a structure that has a known and fixed length. The way you get out of that, right, is the struct is only containing the pointer to the address of where the actual string content lives. It contains exactly 8 bytes in the struct for that address. And then I, as the programmer, am responsible for somehow or another allocating some space for the string somewhere else. And we'll see different ways to do that. But the other thing is these strings are going to need to outlive the function that reads and parses them. So we are going to use heap memory and malloc and its friends for doing this. So we're going to try to just wrap malloc with this like wrapped array class I just sort of wrote for this. It's just going to store a pointer to our array. It's going to store the number of items currently used and also the number of items currently allocated. Thank you. And basically, by tracking the number, the usage and the allocation separately, it allows us to over-allocate, which allows us to invoke realloc much less frequently. The thing with realloc is because arrays do have to be in a single contiguous region of memory. If there's some other thing on the other side of them that's blocking you from growing into that space, it will just have to be copied and relocated somewhere else. That can be quite expensive. I've seen it take 50, 60 milliseconds, which is no garbage collection pause, but if we're doing it 86 million times, you don't want to eat that cost 86 million times. So instead, we're going to grow by very large chunks. So basically, we can have a tiny little factory helper and a wrapper around realloc that hide some of the casting and take type parameters. I'm a little behind time, so I think I have to go quick. Qsort is also worth looking at quickly, though. This is as close as C gets to generic programming patterns. In that it'll sort an array of any type you care to throw at it. But instead of taking like a type parameter like a Scala method would, instead it just takes a pointer to bytes, but it also takes the number of items as well as the size of each item. And then you pass in a comparator, which is actually a function pointer. C, of course, has function pointers, but Scala makes them so much easier to work with. And then the comparator is actually responsible for doing the casting from pointer byte back up to whatever actual type. So if we want to sort our engrams by descending by count, we do it like this. I don't have time to linger on this, unfortunately. Going a little slow. So I went really aggressive and allocated a million items at a time. So we're going to allocate about 20 megabytes in chunks, but we have 2 gigabytes of data to hold around. So I actually think that's a fair optimization. And otherwise, the data is pretty similar. We iterate over standard in with fgets. We check to see if we need to grow the array. We do. And once we've ensured that we have space, we can parse, and I'm going to write the parse line function in the next slide. We can parse directly into the block of memory indicated by the next free item in the array, which is just array.data plus array.used. Sort of awesome when the pointer arithmetic is clean and actually works like this. Once our array is filled up, we just call qsort and then print it out. I was surprised by how little code that took, actually. And then parse line is actually easier than our parsing from the last example. In fact, I'm taking 4 extra lines just to break the fields up, just to get around the tuple notation. I'm literally using scanf directly into the array, so it's just reading them right into place. One cool thing that's in standard C now is you can ask scanf to malloc string storage for you with this ms modifier, which is a really cool little trick and made this way faster to write and easier to fit into some slides. So how does this perform? So they're within a few hundred milliseconds initially. The JVM actually does the sort faster, but native catches up to it on I/O. Native wins by a fraction, right? But native continues to sort of win as we throw more data into it. And it's not actually until you get to about 700 gigabytes that native sorting is actually faster than the JVM. The JVM is really good at jitting tight inner loops that are running millions of times comparing integers, right? It's going to be hard for any fully AOT compiled program to beat a tight inner loop in a quick sort, right? But if you give it enough data, we can. And here, what's really interesting is how this totally goes off the charts as we proceed. And after I got to about 1,100 megabytes, the file wouldn't sort on my laptop with a 7 gigabyte Docker VM. Whereas native, it's slowed down a bit. Sorting's not linear, and it's not going to be linear, but it still maintains consistent performance, even as the heap grows quite large. So I was pretty happy with that. I love this really neat aggregation example. I don't think I have time for it. In fact, I know I don't have time for it. The cool thing is that if you pre-aggregate your data to get the size of the array down by 2 orders of magnitude, Native starts winning at the sort performance again, even at the smaller data sizes, because it's not giving the JVM time to warm up, actually, which I thought was a neat little finding. But again, similar trends and a fun application of allocation hacks. So that concludes the empirical portions of my talk. Now I get to wave my hands and make vague generalizations, which is my favorite part. But I think there's a pretty clear argument I'm making here that there are benefits to using a C-style memory model within the context of a larger garbage collected programming environment. I'm not saying we should only write code like this, but there are clearly cases where it makes a significant difference and not an incremental one. And also the JVM's memory model doesn't seem like it works really well when you're doing a lot of I/O and you have a really big heap, which is, again, maybe obvious, but worth calling out, actually. And this is that governs how I think about where Scala Native really could make an impact, in addition to where it's already hitting with command line tools. Now, with the caveat, performance isn't everything, right? I don't want to trade off safety or stability for performance. Unsafe memory is called unsafe for a reason. It's really hard to do this right. I definitely overflowed some buffers and seg-faulted when I was writing this. C programs are great when they're little artisanal code written by one person in a few sittings. But giant C code bases are a nightmare. But we've also gotten much better at writing good delivering software in small programs, right? In a way that wasn't possible a few years ago, like containers and Kubernetes and things like that. I don't want to throw around dumb buzzwords, but writing small programs that compose is really awesome, and it makes techniques like this more palatable, right? The other thing is that the Scala community has gotten very, very good at metaprogramming in the last few years. I think we've surpassed the Lisps finally at this. And it opens up some new opportunities. So here I'm just going to sling some citations at you. Tjark Ramph and Nada Amin have these 2 really cool papers, both of which are actually compiling Scala to C with this lightweight modular staging plugin. This one in particular is breathtaking. It's 500 lines of Scala, it's clean code, and it feels like magic, right? But the really neat thing is the follow-up, LMS verify, which takes a parser combinator, writes an HTTP parser in the parser combinator, and then emits not just C code, but also a proof that verifies the memory safety of the generated C code. That seems like a really powerful technique, right? And if we could target Scala Native as a staged programming target rather than C, I think it's something we could conceivably write quite a lot of really, really good software in. And once I finish writing this introductory book on systems programming, that's certainly where I would like to see things going. I guess the reason this seems really relevant to me is that, in fact, a lot of the Scala people write are, in fact, in this large heap, lots of I/O domain, right? I use Spark and Akka and Kafka every day. I love them, right? They're great. But I'm also worried that they're going to struggle to keep up with some of the hardware changes that are coming now. I think Intel started shipping these non-volatile DIMMs this month, honestly. Right? These are durable, byte-addressable storage. They don't cost that much more than DRAM, and they are not that much slower than DRAM. So all of a sudden, you have this heterogeneous heap where you want to keep things that look like objects, but you certainly don't want to garbage collect them because they're supposed to stay around even after your program exits. Other programs might be reading to them. You could even read and write to them over a network. And I think it's going to change and break just about everything. There's this Dragojevic paper that came out of Microsoft, which I'm still trying to make sense of because it really does seem to break the CAP theorem. I think the idea is if you're doing remote direct memory access, your NIC is writing into a ring buffer on the NIC of some other machine, you don't have the asynchronous network that the CAP theorem presumes. You actually have a synchronous network on non-reliable commodity Ethernet. Which I think is how it gets around it, but I think this is really exciting, honestly. And yeah, so with that note of if I'm going to be directly writing into the memory of other machines, I certainly want something that gives me direct like pointer arithmetic and buffer access, like Scala Native does. Which is why I hope that if we do have to make that kind of hard break with the past, then Scala Native isn't a step back to where we were 40 years ago with C. It's a step forward into whatever this strange new thing is. And that's my talk. Thank you.